Okay, so now, as we have seen, if we go back to our relations, okay, once we find the value of our corresponding friction, we can calculate V because we have a relation between F and V. So now V is known, okay, and the corresponding flow rate in my pipe can be calculated, okay. So here the question was to find, we go back to the question. The question was to determine the airflow rate, okay. So here, guys, so here it's not water, it's air, okay. Air is flowing inside the system. So we can calculate the corresponding flow rate, okay. So that's it. This is for the first problem. Any question on it before we move to something else?
Doctor, there was just a small question. أول شيء على قصة إنه
Yeah.
كان I think محمد كان عم يسأل إنه V1 غير V2 غير ال V.
هن ذاتهم هون. Why هن ذاتهم هون? Because you
هون
have
الفرق
one.
بينهم بذاتهم.
Because you have one diameter, okay. You have one, the diameter of your piping system is the same. So you can say that at any location, you have the, it's not zero, it's equal, okay. So we can simplify that. So you can say that since D is constant, okay, and we can consider incompressible flow, rho constant, okay, then we can say that A times V is a constant. And since the diameter is not varying, because D constant, we can say A constant. So we deduce that V is the same everywhere, okay. Now what will happen, okay, if you have several diameters, change in diameter, here it will be more complex. So in this case, if you have variable diameters, when you calculate here, let's say the friction, you should divide your segments. For each segment where we have a new velocity, you should take it separately. Okay, so it becomes more complex to work. But since it's one same velocity everywhere, so so V1 equals V2 equals to V. Okay.
هون ال V اللي بقلب اللاسز الماينر والميجر هن الفيلوسيتي بقلب ال V مثلا او
هي
هون بسبب
average
ال V هي ذاتها.
velocity. It represents the average velocity in the cross section. هي ذات. اوكي، هي velocity over، اذا بدك مش انت اخذ L over D، انت over a certain length you have a certain velocity. It's the average value over this length. But here you have that the velocity is everywhere. بالضغط you have the piping system, the velocity everywhere is the same. So V average is equal to V1 equal to V2. اوكي
دكتور اذا كان variable كيف بنطلعها؟
اذا كانت variable هعمل لكم examples. مثل ما قلت لك بصير بدك تقسم البروبلم ل different steps. اوكي Another example. So here we will see another type where we want to find the volumetric flow rate also, but the unknown is our difference. Okay, so we have a turbine that's shown in the figure, extracts 50 horsepower from the water flowing through it. The 1 feet diameter, 300 feet long pipe is assumed to have a friction factor of 0.02, and minor losses are negligible. Determine the flow rate through the pipe and turbine. So here it seems that we have several simplifications, because first they gave us F, so the friction factor is given, no need to do any assumption, it's 0.02, okay, and no minor losses. So when we write our equation, no minor losses, we only have the major losses. Okay, and since we have a turbine, we should pay attention that the turbine will extract energy. Okay, because it's a turbine, then when you put H turbine, you will put it to the side of second side 2. If you have a pump, you put H pump from which side? From the first side, because the pump will give you energy while the turbine will take from the water energy. Okay, so the energy equation for this system between 1 and 2 is P1 over gamma plus V1 square over 2G plus Z1 equals to P2 over gamma plus V2 square over 2G plus Z2, but we should add two things now. Since we have a turbine, we should add H of T, okay, which correspond to the turbine head, and we should add HL, which represents the losses head. Okay. Now, for HT, how to determine H of T? Since they gave us the power of the extracted from the pump, okay, you know that power, what is the unit of power? The unit of power is watt, okay? If I am watt. So if I have, let's say, from dynamics, if you remember from dynamics, when you calculate power, one of the method is to do F times velocity, okay? Or here, because we have pressure, we can replace F by pressure times area times V. So this is why for power, so here I will put power to not confuse P, okay? Power is pressure times what? What is AV? It's the volumetric flow rate. So power is pressure times Q, volumetric flow rate, okay? So since here they gave us the extracted power of the turbine, okay, we can say by replacing P by gamma H, so pressure, the corresponding pressure for the turbine is gamma times H turbine, okay, times HT, okay, times the Q. So if you want to get H of turbine, HT will be equal to the power over gamma. Of course, gamma is of the fluid. Here it's water, so we use gamma water. And we multiply by, so over gamma times the volumetric flow rate Q. Okay? But what is the problem here is that we don't have the velocity. So we don't have Q also. So here V is unknown. Okay? So let us go through the equation. Okay? So first, P1, 1 is exposed to the atmosphere. So if we are working in gauge pressure, we can say P and 1 and 2 are exposed to the atmosphere. So as you can see here we have water exposed to atmosphere and we are exiting to the atmosphere. So we can say that P1 equals to P2 equals to 0 gauge pressure. This is why these two terms will cancel out. Okay. Now, for V1 and V2, here in this example, V1 is different than V2. Okay. So you have V1 is nearly 0. Why? Because you are taking water from a very large reservoir. So the area here, A1, is very high compared to A2. Okay, so we can say that V1 is much smaller compared to V2. And then we can nearly take that V1 is nearly 0. Okay, so this term also will cancel out. Now, concerning the change in elevation, here they gave us the elevation, so we will put them. So here they considered that the reference is at the lower level. Okay, so if your reference for Z is here, they said that Z2 is 0 and Z1 is given to be 90. So you replace Z1 by 90 and Z2 is 0. Okay, now we still need to have idea about V2, HL, and HT. Okay, so let us try to figure out how to express these terms. To start with, the losses here are major losses because they said we neglect minor losses in this problem. And why we are neglecting, as I told you, when you have a very high length, a system of very high length over D, and the ratio L over D is very high. In general, the major losses will be dominant over the minor losses, so we can neglect them. So here, the losses are given by F times L over D times V squared over 2G. Now, the friction factor is given, the diameter is given, but the problem is with the velocity. V is not known, okay? I don't know the value of V. And V is equal to V2. Why? Because we said that V represents the average velocity in the duct. And as you can see here, if you go back to the figure, so my duct here, for the whole duct, I have the same diameter. So the velocity at 2 will be equal to the velocity at this section here. So from here to here, same velocity due to constant flow rate. Okay, so I can say that, of course, the average velocity in this part will be equal to V2. So V, average velocity in my duct, is equal to V2. Okay, so now my unknown is V. I don't know V. So my first energy equation gives me what? Like the previous problem, it is giving me, but here what I know, F is known. What is the good point in this problem is that F is given. So because F is given, then if I replace in my equation, I will get only one unknown, which is velocity. Why? Because we said that V2 is equal to V, and we express the major losses function of V. We still need to find H turbine. And as we said together, what is the head of turbine? It's the power over gamma Q. But Q can be expressed as a function of V. Okay? So by replacing Q by A times A, it's the area times velocity. Okay, and the area is, of course, it's a circular area, so it's pi d square over 4, so pi d square over 4, and also the diameter is given, so this will simplify things. Okay, so times velocity. So now all I have to do is to plug my HL and HT into my equation. I will get the following relation, and as you can see here, the only unknown is velocity. So all I have to do is to solve my numerical equation and get the corresponding values of D. Now, what is interesting here, I will obtain 3 solutions, 1 negative and 2 positive. The negative solution will be rejected because I'm talking about magnitude of velocity, which should be a positive component. But here, why I have 2 solutions? I have one that is relatively low and one that is relatively high. So if you want to do the analysis of this, what will happen here? When you have increased velocity, when V is higher, Q will be higher. Yani the volumetric flow rate is high, but on the other hand, also the friction HL will be high, which will reduce HT. Okay, because at the end, HT, the turbine head, okay, is proportional, if you want, is proportional to Q, but at the same time, if you write it in the energy equation, it's inversely proportional to HL. Okay, so this is why here, when I have high V, I will have a higher Q, which is good for me, but also I will have a higher losses, higher HL, which will reduce my the possible value of HT I can get. Okay, and on the other hand, I have if I have low velocity, it will be the reverse thing. Okay, so here we have, if you read it in the command, they are telling us that for either the 2 flow rates will give us the same power, because the power is gamma QHT. So as you can see, for the power, if you increase VQ will increase, but also HT can be reduced because of the losses. Okay, so here, for example, when you take the small velocity, okay, when you take the velocity of 6.58, what will happen is that the losses are only 4.04. You have low losses because of your low velocity, and this will give you a relatively high value of HT, but Q will be lower. Okay, Q will be 5.17. On the other hand, if you have a large velocity, Q will increase. It will increase from the second solution will give you a higher Q, which is 19.6. But on the other hand, it will give you higher losses also, and higher losses will induce lower turbine head. And at the end, the power is the product of Q times HT times gamma. So the 2 solutions will give you the same product, but one will give you a higher Q, one will give you a higher HT. Okay, so this is the analysis why we can have 2 possible velocities to extract this power from the turbine. Any question on this problem?
In real life, which one they tend to use?
Look, sometimes it will depend. Of course, if you can go with small velocities and reach the same solution, so it's fine. Okay, because always you can have unpredictable losses. Like here, we neglected the minor losses. Okay, so if you take them into consideration, this might need to a lower power. This is why you can work with the smaller velocity, because it will reduce. If you have minor losses, they will be reduced with a smaller velocity.
طيب وإذا we neglected minor losses أخذنا ال HL اللي
if
هي
you
major losses
neglected
وال
if you
HT
neglected
كانت شو؟
اثنيناتهم بيزبطوا. two velocities بيعطوك نفس الباور.
إيه أنا I mean إنه إذا we took into consideration major losses ال HT كرمال شو؟
نحن we took into consideration التربين. انت if you put a turbine in your system it will extract energy. This term is due to the...
نعتبرها a third loss يعني.
yeah هلا هي بالحقيقه منا loss، بالعكس انت بتستفيد منها. اوكي مش هيك ما بيحطوها مع اللوس.
ايه بدها تعطي غير شيء
لانه you are using this energy. This is why they take it as separate term. انه it's a useful energy that I can use it somewhere else. Okay, and if you have a pump بتستعمل HP and you put HP from the first side, from side 1, because you are giving to your system energy, not taking from it. Okay, يعني هون إذا برجع على energy equation here. This is your energy equation. If you have a pump involved in your system, you will add it from this side because the pump will add to your energy. While if you have turbine, you put it H of turbine from the other side because it will extract from your energy. And the losses are always, we put them from the second side because they will reduce the energy of my system. Okay? Another problem. Another type of problems we can have. Air at standard temperature and pressure flows through a horizontal galvanized iron pipe. So here, for example, they gave you epsilon, but فيهم ما يعطونا إياها، فينا نجيبها من التable because it's galvanized iron. So we can get like the previous problem one we did. We can get the value of the corresponding value of epsilon, and they gave us here the flow rate. Okay, so here the flow rate is given. The pressure drop is not to be more than 0.5 psi per 100 feet of pipe. Determine the minimum pipe diameter. So here, the only thing that we changed is the inputs. So instead, in the previous problem, they gave us the diameter and we need to find the flow rate. Now, they give us the flow rate and we need to find the diameter. So in general, these problems follow the same method, but the inputs vary. Okay, and depending on the inputs I have, I decide on what to do. So first, as usual, always start with writing your energy equation. Here it's relatively a simple case because no minor losses, and it's just you have a straight pipe because I said horizontal. Okay, so I have a straight pipe in a horizontal plane. They didn't mention anything about accessories, about bands, so no minor losses. They gave me the length of my so for 100 feet, I have a pressure drop given. The pressure drop should not exceed 0.5. So here I have a limit for the pressure drop. So I should design based on this limit. So of course you know that reduced diameter, logically reduced diameter will increase losses. Okay, because you are restricting the cross section, which will cause more losses. This is why also you can get it from the expression. You know that the major losses are equal to F times L over D, okay, times rho V square over 2. So D is here. When you decrease D, your loss, this term will increase, okay. It will increase for two reasons, because you have D here, and at the same time, when you decrease D, V will increase. So what will happen for the major loss, they will increase a lot, because the reduction of D for the same flow rate will lead to an increase of V, and this will give me a very high increase in the major losses. Okay, this is why here they said what is the minimum diameter to use, because I don't want to exceed a pressure drop of 0.5. Okay, so here they give me P1 minus P2 maximum, and I should design what will be the corresponding minimum diameter. So for the energy equation, it's here very simple. No, as we said, no minor losses, same level, so Z1 equals Z2, horizontal plane. Because I have one duct of constant cross-sectional area, V1 is equal to V2, equals to the average velocity V. So also the V squared over 2 terms will cancel out. So I will only end up with this relation. And since delta P is given in the problem, so this is P2 minus P1 maximum, they give me P1 minus P2 maximum. So, and I want to design for the minimum diameter. So I get my first relation, okay? And as you can see here, I have two unknowns, V and D, but of course, so this is my first relation, and I can relate VD through volumetric flow rate, okay? So in this relation one, you have as unknown V, D, and what also, and the friction factor F, okay? So as a first step, to relate V and D, which relation I can use? I can use the volumetric flow rate. So always, as I told you, think first of the energy equation, then think of using the volumetric flow rate equation. So Q is V times A, since I can treat my flow as incompressible. So I have VA, okay? And since here the area is variable and V is variable, but Q is given. It's given to be 2 feet cubed per second. So I can get a relation between V and D, okay? So this is equation number 2. Now, if I continue, you know that for a problem, okay, so here I have until now 3 unknowns and only 2 equations, okay? So let us continue. If I want to use the Moody chart, I need what? I need my Reynolds number, okay? So since I need my Reynolds number, I should express it in my problem, but Reynolds is function of D, and D is unknown. Yani Reynolds is function of V and D, but V can be expressed function of D from equation 2, because Q equal V times A. So Reynolds can be expressed as a function of D also. So what I got until now is that if I replace in my energy equation V square by its function of diameter, I can find a relation between the friction factor and the diameter. And by writing the relation of Reynolds, I can also relate Reynolds to the diameter. So these 2 equations, the combination of these 2 equations will give me 3 unknowns, but with only 2 equations. And the other factor that is important in Moody chart is epsilon over D, okay? So you can see here that for my 3 factors involved, okay, I have 2 unknowns, which are F and, so F is unknown. Reynolds is unknown because it's function of D. And epsilon over D is unknown. So this is the worst case scenario. So I don't know F, I don't know Reynolds, I don't know epsilon, but all I related to D. And if I find D, if I just find D, from equation 2, I calculate F. From equation 3, I calculate Reynolds. From equation 4, I calculate epsilon over D. Okay? So the tricky issue is that I should have the value of D. What we can do assumptions. So first, I should do assumptions here. But I have several choices for assumption. I can assume D. I can assume F. Okay? In general, okay? We will in general we are used to assume F, okay, but we will see that sometimes it is possible, sometimes it is always possible, but sometimes it can be complex. Now if I look at my relation, the relation between F and D is straightforward, so I can assume F, and from F I get D. So it's good idea to assume F, okay, because F always we have some ranges, yani some typical values. Yani wholly you will learn them from experience. So a typical value for F, when you don't have epsilon over D, you can start from F. It's a good start, 0.02, because it's just at nearly the middle. Yani if I go to the Moody chart, let me go to the Moody chart. Okay. So here, not like the previous example. In the previous example, we know epsilon over D. When you know epsilon over D, this will facilitate a lot. You start directly from F corresponding to the flat curve. But here, epsilon over D is unknown. So a good strategy then will be to take a value of D. And from application, and from real life, a good estimate to start with is 0.02. So in general, if you don't have anything given, and you want to start by an assumption for F, 0.02 is a good part to start with, okay? So what should I do if I assume F 0.02? If I did this assumption, I don't have, I should find what is the corresponding value for the other variables, okay? So you know that I wrote my equations here. I have these two equations here, d function of f and Reynolds function of d. So if I did an assumption for f, if I replace in equation 2, okay, so by assuming f, I start by f0. So assuming f0, okay, equals 0.02, okay, I can calculate d0. What is d0 for this value, for this f? And then obtaining d0, I plug it in equation 3 here. I get Reynolds 0. Okay. So now, once you have Reynolds and you have d0, if you replace d0 here, you can get epsilon over d0. Okay. So now, what you will do to verify if your assumption is right or not, since you assumed f, you should now find the new value of f. So now I have a Reynolds number. I have a certain assumption for epsilon over d. I go to what? I go to my Moody chart. I plug in my Moody chart Reynolds and epsilon over d, and I find what is the corresponding value of f. So here, let us take the numerical values I found. Okay. So by assuming f equals 0.02, they got that Reynolds is 8.76 times 10⁴, and epsilon over d is 0.0027. So what I will do, so here just what I will do, I will take these two values and plug them in the Moody chart. Okay, so let us do this together. So keep in mind the values, 0.0027 for epsilon over d and 8.76 times 10⁴ for Reynolds. So let us go now to the Moody chart. As you can see here, first, the red line will correspond to Reynolds of 8.76 times 10⁴, and the curved green line correspond to 0.0027. Okay, as you can see, the intersection of the two lines is nearly here. This point, I put X for you. This is the X I put. So if you take a horizontal line to read the value of V, you will read a value of 1 equal to 0.027, which is far from, so this value is far from F0, which was 0.02. So I say I cannot stop here. I should do an additional iteration. Okay. What to do now? Since I found F1, I plug into first equation, I get D1. Okay, so now I get D1 from equation here. I think the number was 2. Okay, and then once I get D1, I plug D1 in Reynolds. I get Reynolds 1. Okay, in equation 3. Now I will repeat, and in equation 4, I get epsilon over D1 from equation 4. Okay, because once you have D, you can calculate epsilon over D. Okay, now you will obtain the new values. The new values, if you plug, will be for new Reynolds, okay, is 8.27. So from here, you can know that I am close, because before I had 8.76 times 10 to the power 4. Now I am at 8.27 times 10 to the power 4. So the difference is not very high. And for epsilon over d, I was at 0.0027. Now, if I calculate, I have 0.0026. So just from here, you can predict that the value of f will be very close. And sometimes, because the chart is not very accurate, sometimes you can not see the difference, okay, as it is the case here. So here, if you take now a line, this one, if you take a new line for the new Reynolds, 8.27 times 10 to the power 4, and you have the blue curve. The blue curve is for epsilon equal to 0.026. Then the intersection is nearly the same at the same place. Okay, so f1 is equal to f2, so I can stop, of course. And even if I have a small difference, I might have the intersection here, for example. If I have like this, if I see that the difference it's nearly, so for example, if you get 0.027 here and here 0.026, so it's fine. I will stop. I can stop that. Okay. So that's it. Okay. this is the method I can solve. So now I can be sure that my f is 0.027, and I can now go back to my problem and I replace my variable by their corresponding values. So here, once you get the real value of f, you replace into this equation, it will give you the accurate diameter d. Okay, and this was the question, to find what is the minimum value of d to not exceed the pressure drop given. So here d should be 0.196 feet. Okay, any question?
دكتور
Yes.
لو عملنا assumption تانية كان طلع معنا Reynolds number fair وإبسلون over D كان طلع fair
مظبوط.
فكان طلع معنا fair فأنا كيف نعرف؟
اوكي بس تعملي several iteration توصلي اخر شيء لنفس الريزلت. يعني انت وقتها توصلي ل percentage difference اقل من 10% for example او 5% let's say, then you can stop your calculation, لانه whatever is your initial assumption رح ترجعي توصلي لنفس الريزلت and you can try it. اوكي، لانه الانيشال فاليو تبعك will not affect the final result, بس تقول لك it will affect what? The number of iteration. يعني if you started by a very far value، يعني بدل 0.02 تنقول if you started from for example 0.09 اكيد حتطولي بالايتريشن تتوصلي اكثر. يعني you might need more iteration to reach your converged solution. But if you start from beginning with a value that is close, then you will not need several iterations to reach your accurate solution. Okay, يعني بس الانيشال assumption بتفرق بعدد الايتريشن، غير هيك no. يعني at the end you will get the final same results.
Okay, thank you.
Any other question? Okay guys, so hopefully we will meet Friday, okay, because we said that we will replace Monday by Friday to give you time to study. And now please, you should cover the last part. So cover the last part of the video for Friday. Yeah, I'll see you next time. Bye.